So first of all, thank you everyone for joining in for today's talk. And we are very happy to host Professor Tanmay Chakrabarti as our speaker for today. He is an associate professor of electrical engineering and associate faculty at the Yardi School of Artificial Intelligence at IIT Delhi. He has been a known name in the academia, and many of you might know him. For those who do not know him, he has been part of IIT Delhi prior to his current role, and he has been heading the Laboratory of Computational Social Systems, which focuses on NLP, computational social science, and machine learning. In today's talk, he will be talking about prompt engineering, specifically how to design good prompts to get better outcomes from the LLMs. And we are very happy to host him today. Thank you so much, Professor, for accepting our invite, and over to you now.
All right. Thanks very much for the invitation, and it's great to be here. And so in today's talk, I'll be basically talking about our ongoing work last 1.5 years on prompt engineering, particularly how you can design efficient prompts for different downstream tasks. Okay, and this is a joint work with my postdoc Subhabrata and my RA Ishan and Jives and one of the undergrad students, Manish. So all of us are aware of the interspectrum of large language model. So the drama started way back 2017 when Vaswani et al. From Google Brain, they proposed this model called transformer, and this is not the electrical engineering transformer. This is a large language model named transformer, and in this paper, attention is all you need. They showed that how you can overcome some of the problems of recurrent neural network by processing a sequence of tokens in parallel using an encoder-decoder model, right? So, and post that, the three giant industries, OpenAI, Google, and Meta, they started designing their own language models, large language models. I would say language models in 2017, 2018, during that time. So OpenAI started building their GPT series models, GPT-1, 2, 3, 3.5, GPT-J, GPT-Neo, and recently GPT-4. And similarly, Google also started designing their models in the BORD series, BORD, Robota, Albert, so on and so forth. Then recently, Lambda, Grapher, GLM, and so on. And then Meta also started designing their models like Galactica, OPT, recently Llama, and so on and so forth. So during the transition phase, like in 2017-18, people actually, the way they train this kind of model, they used to train this kind of models. So they first pre-train their models on tasks like masked language model or causal language model. Then they fine-tune their model on a downstream task. Let's say the task is sentiment prediction, or the task is say machine translation. So you have limited amount of training data. Now you fine-tune your models, update your parameters little bit so that the models would be aware of the task that you want to perform, and then during the inference time you predict. Then GPT-3 came in 2020, and GPT-3 paper, they actually noticed a very surprising fact, which is something called prompt, right? What is this prompt? So what they showed is that if you kind of instruct the model using simple natural language to perform certain tasks without doing fine-tuning, right? The model basically performs quite decently, right? And this was interesting because the model was actually pre-trained on a very generic data set, very generic kind of task, masked language model or causal language model. But now the model has learned something very nice, which would basically lead the model to do all sorts of downstream tasks, right? By just writing a simple prompt. Now, let's say, and what would this prompt look like. Let's say the task is sentiment prediction. You can just you can basically put some examples within a prompt like this. That movie was great, sentiment positive. It was a horrible movie, sentiment negative. This is an absolute mess, sentiment, and then the model will predict. Hope the model will predict the next word as negative, right? So this brings us to a new paradigm, which we call as pretrain, prompt, and predict, right? There is no fine-tuning task as such. Through this prompting, if it is a few short kind of learning, through the prompting, you let the model understand the task that you want to perform using the kind of exemplars, demonstrators like this, and hopefully the model would be able to rightly hit the part of the memory which is responsible for doing sentiment analysis, for example. Now, we do not know how the memory, right, the internal memory, the parametric memory, the so-called parametric memory is actually designed or is actually trained within the large language model. So we do not know which part of the memory is responsible for sentiment analysis, which part of memory is responsible for, let's say, machine translation, and so on and so forth. But the hope is that through this exemplars, the model should be able to understand which part of the memory should be responsible and the which part, which kind of parameter, set of parameters should be fetched further for the downstream task. Okay, so let's look at the prompting in general. So prompt, as all of you know, basically, the prompt is written on top of a pre-trained language model. Pre-trained language model, a language model is pre-trained on generally either of these tasks. The first one is masked language model, where given a sentence, you've given a sequence, you basically mask out certain phrases and let the model predict those phrases. In case of mostly in case of encoder only models like BERT, Robota, this kind of masked language models based pre-training is very popular. Whereas decoder only model or encoder decoder only model like GPT series or encoder decoder models like T5, right? We generally use the causal language model or autoregressive model, where we let the model predict the next word given the context, right? So now if you look at and in prompting in general, the hope is that with prompt you can do all sorts of tasks. It can be a simple question answering task or fill in the blank task like JDK is developed by Dash, or it can be a summarization task like this is a super long text, TLDR, right? The model should be able to write the TLDR of the long text, or a common sense visiting task like birds can dash, birds can fly, right? This is a kind of a world knowledge that the model should know to answer this kind of fill in the blanks. So if you look at prompting in general, prompting is prompt is generally written in two ways. The first one is more of a, no one writes hard prompt these days. Mostly prompts are written in supervised manner, where some part of the model, some part of the prompts is being trained during the fine-tuning phase. This is basically soft prompt or kind of continuous prompt, where in an ICL context, in context learning paradigm, you basically give a exemplar, set of exemplars or demonstrators, and then the test example, and then you expect the model to predict the corresponding level of the test example, right? In this case, there is no fine-tuning happening, and there is no, there is no update of the prompt that you have written, right? So now prompt engineering, as you all know that, these days all big industries hire people who are quite familiar with writing good prompts. So prompt engineers are of ultimate demand these days. But one should also know that all these large language models are very fragile, in the sense like these models are sensitive to prompts, very, very sensitive to prompts. For example, if let's say the task is sentiment prediction again on movie reviews, and you write you basically write a prompt like this, that that movie was really great. If you are dumb beyond imagination, kind of a sarcastic, prompt, and you want the model to predict the sentiment expressed in this above sentence is. So the entire sentence, the entire context is the prompt. And if you pass it through a Bloom kind of model, you will see that the model will predict on the positive side of the range. Now this is the prediction, and from this prediction you can infer the sentiment of the prompt, right? If you slightly change the prompt in this way, now this is your prompt. The movie was really great. If you were dumb beyond imagination, within the quote, the author's opinion expressed towards the movie in this sentiment is, right? And you pass it through Bloom, and Bloom will predict it the next word as neutral. You see a slight change in the writing style of prompt would actually give you a different sentiment altogether. If you write in this way, the same sentence within a quote, the author's opinion, in the author's opinion, comma, the movie is, the language model will predict not good. Okay, so you see with slight change in the, in the English of the prompt that you have written, the model will essentially predict different things, and it basically predicts all sorts of sentiments, positive, neutral, and negative. So therefore, it is very important to, understand or to know how to write optimal prompt. So we started our research 1.5 years back from this part, from this premise, and we basically hypothesized. We started with a simple hypothesis that a prompt, the prompting should work better if the task is similar to the pre-training objective. Let's say the pre-training objective, let's say the task, the downstream task is fill in the blanks. Okay, and this fill in the blanks, this blank space can appear at any place within the sentence, within the sequence, right? Now, if you pre-train your model using, say, causal language model paradigm, autoregressive setting, your model won't be able to understand this properly. So since your downstream task is fill in the blanks, you should, the pre-trained model should be, pre-trained on the MLM kind of task. If your task is to, let's say your task is to kind of a machine translation kind of thing, your pre-trained model should be, pre-trained on a causal language modeling kind of task, right? So in our first contribution, in our first paper, we showed how you can align the pre-trained, the pre-training paradigm with the task that you want to perform, right? So you have certain downstream tasks. You want to pre-train the model, which should be aligned to the task that you want to perform. This is the first part of the contribution. The second part of the contribution is how you can design an optimal prompt, which should also be aligned to the task. Okay. So the second, the second observation, the second contribution is in a kind of a cross-lingual setting. Let's say you have a lot of data, you have a lot of training data in English language, and you want to perform a task in Hindi language, assuming that Hindi is a low resource language. So you write the prompt in English, and your test set is in Hindi. You want to predict the sentiment of the test set in Hindi. Okay, so your prompt is written in English, your test set is in Hindi, and you basically want to perform the task on the Hindi sentence. So in this kind of cross-lingual setting, how you can design optimal prompt so that in the target language, which is Hindi in this case, the model should be able to better predict the labels. Okay, so let us start with the first one. So the task, remember, the first contribution is to come up with a pre-training strategy which would be aligned to the task. Okay, and the task in this case is called argument mining or argumentation mining. I will discuss what is argumentation mining. And the second contribution here is how you can design the prompt so that it is aware of the task that you were about to perform. Okay. So what is argument mining? Argumentation mining is a kind of an old task in natural language processing, where you are given a discourse, a kind of a discussion. You think of it as a Twitter, as a discussion happening on Twitter, or a discussion happening on Reddit. Two or multiple parties are interacting with each other, and basically in this case, your first task would be to identify the spans, the important spans responsible for this task, and then the second task is basically to classify the spans into two categories. One is called the claim, the other category is called premise, right? So for example, in this case, you see here dummy example here, right? This is the first utterance, uttered by a speaker, and you see in the first line, the red colored line, EMTs, SAR, fighters, police, etc., should receive military discount. Okay, this is the claim, and the premise is as follows. It's common, at least in the US, for businesses, transit agencies, etc., to give small discounts to military veterans to thank them for their service. So this is the premise. Based on this premise, the speaker actually claimed this. So the first, and remember, there are significant gaps between a claim and a premise, right? And a claim or a premise may not be the entire sentence. It can be a part of the sentence. So the first task is to identify the span, which is a claim or a premise. The second task is, given the span, can we identify whether this is a claim or premise? The third task is, given the claim and premise, can we figure out the relation between them? Let's say there is a pair of claims. There are two claims. Can we say that the second claim is supporting the first claim, or the second claim is opposing the first claim, or so on and so forth? Or it can basically find a relation between a claim and a premise. So you have a pair of claims, you find a relation between them. You have a pair of claim and premise. You basically find out the relation between claim and premise. One can also think of a relation between premise to premise, but in general, in argumentation mining, we do not care about the relation between premise to premise, right? And these are the relations that we are interested in. And these are very standard, standard tasks. The relations are support, agreement, direct attack, undercutter, and partial. Okay, so three tasks: span detection, claim and premise identification, and the relation prediction. Okay, now what are the problems here in this case? The problem here is that in the argumentation mining literature, you have very limited amount of marked or label data, right? Label span data, label relation data, and so on. The second problem is that there is no uniform data set which contains both the claim premise as well as the relation. Okay, so then the question is, let's say you have 1,000 or 2,000 such label data set. If we use 1,000 such data sets to fine tune your model, you take a pre-trained model, you fine tune your model with this 1,000, 2,000 data sets, it is not enough. Your model will not learn anything because you have a billion size models and you have a minuscule data set, right? So then what we thought is that, can we leverage huge amount of unlabeled data available to us? Let's say you can scrape the entire, you can scrape the entire Reddit dump is available, so you can use them, and you can also scrape data from Twitter. You do not need the labeled data, right? So can we use this unlabeled data in a systematic manner so that the model that you're going to use would be aware of the task that you are willing to perform? Okay, so in the first step, what we did, we basically used the unlabeled data taken from subreddit, right? This is the subreddit thread, change my view. Generally, people use this thread for argumentation mining. There are discourses, right? And then what we did, we came up with an idea called selective mask language model, SMLM, right? Remember, we have a pre-trained model. The pre-trained model can be, let's say, a bot kind of model. We took a pre-trained model, then we further fine-tuned it in an unsupervised manner using this kind of SMLM technique, right? What is this SMLM technique? So instead of, we know that the model was already pre-trained on a masked language model, right? Randomly, during the pre-training stage, someone randomly dropped some of the tokens and model had to predict those tokens and so on and so forth. So model doesn't have any idea about argumentation. What we did here in the literature, it was shown that there are different argumentation mining markers, right, which are responsible for the task. And what are these markers? The markers are like IMHO, in my honest opinion, in my opinion, right? So my belief, I think, yet, however. So these are the markers which are responsible for argument, which basically serve as a very important cues for argumentation mining, right? So we took a pre-trained model, we manually curated, a bunch of such markers responsible for argumentation mining from the literature. We basically then designed a kind of a model which can further augment this list. We have a list of manually curated such markers. We have a model which was trained on this list. And the task of the model was to come to basically extract similar such markers from the Reddit data. And then we started augmenting the list, right? Let's say we have now a list where some of the markers are curated manually, some of the markers are curated using this third-party model. Now, what is this model? That's not important. You can use any model to curate such kind of markers. In the selective masked language model, then what we did, we basically masked these markers, and we wanted the model to predict these markers. So we wanted the model, to understand these, particularly these markers for the downstream task. So now the fine tuning, well, you can call it as fine tuning. You can also call it as pre-training, doesn't matter. But now the fine tuning is happening using the selective masked language model paradigm for the particular task, keeping in mind the particular task, which is argumentation mining in this case. So your model is now pre-trained on this SMLM task, right? For this kind of pre-training, we basically used two models. The first one was Robota, and for the Robota, the context was a particular utterance, and we also used longformer. In longformer, we all know longformer, basically a variation of transformer where the context can be of a large size compared to Robota. So in longformer, we basically put the entire thread as a context. So remember, this is a Reddit post, so you can think of the entire discussion as a kind of tree-like structure where a thread can be taken from the root to the leaf, right? So in case of longformer, the entire thread was given as a context. In case of Robota, we basically gave individual utterance as a context, right? And we wanted the model to predict the mask tokens, right? The markers basically. So, and once the model was pre-trained on this kind of task, remember the task is the final task is to identify the portion, the span, right? For span identification, on top of this mask, this fine-tuned model, we essentially use a CRF, linear layer followed by a CRF conditional random field model. And then the purpose of this CRF was basically to predict these 5 tokens: beginning of claim, intermediate claim, beginning of premise, intermediate premise, and others. Okay, these are the 5 tokens that we wanted the CRF model to predict. Remember, we have small amount of label data for argumentation mining. We can use the label data for just fine-tuning the top layer of the linear layer of the model, or if you want, you can also fine-tune the entire model. But for our case, we basically fine-tune the last layer. Okay, so CRF was used, and then we basically identified these 5 tokens: beginning, intermediate, claim, beginning, intermediate, premise, and others. And using these tokens, you can now identify the span, claim span, premise span, and others. Okay, so now let's look at the result. Okay, so this is our model, span, the masked language model, selective masked language model, long former based, base long former, where we just took a standard long form model and we used a CRF on top of this, and we wanted the model to predict the different tokens. Then we have our strategy SMLM followed by Robota, limited context, standard vanilla Robota, and then bot and LSTM. You see that with SMLM as a fine-tuning technique, the model performs quite well compared to the base, the base long form model. Okay, so this is the first task. Now, what's the second task? The second task is to predict the relation. Okay, we identified the span. We also identified which span is claim, which span is premise. Now, the second task is to identify the relation between spans, or relation between a span, a claim and a premise. Okay, so for this, we basically tried to come up with a prompt which is aware of the task, right? Now, let's see how to write an optimal prompt which is aware of the task, the task that we want to perform, the relation prediction task, as well as the prompt is aware of the fine-tuning strategy, the SMLM strategy that we came up with. Okay, so for this, let's say these are two utterances. The first one is uttered by user 1. The second one is uttered by user 2. And the first one is this red portion is the premise, and the green portion is the claim, right? And our task is to figure out the relation between a claim and this claim and the premise. So the prompt, the prompt basically it was manually curated. The prompt that we curated here in this case looks like this. You have the entire context. In case of a long former, the context is the thread. In case of Robota, the context is the single utterance. User 1 said component 1, mask, 3 mask. User 2 said component 2, right? You might be wondering why the prompt looks like this. So the context, we know the context is needed. Therefore, we basically prepended the context. User 1, user 2 are two discourse markers because we wanted the model to understand that the first part was uttered by a user, second part was uttered by another user. Remember, we did not use user 1. We basically took a representation of user 1 and then we replaced here. And then why this 3 masks, right? Why not 1 mask? Why not 2 masks? So remember, in the SMLM fine-tuning strategy, we basically mask out this markers, right? Argumentation mining markers. And we observed that the average length of the markers that we like the number of tokens in the, within the mask part was 3, right? The average length. So therefore we thought that if we put 3 masks here, and if we let the model figure out the embedding corresponding to this mask, and then on top of this embeddings, if we just concatenate the embeddings of these 3 masks, we pass it through a linear layer and we let the model predict the 5 relations: support, attack, right, undercutter, and so on. Then it might be useful. Remember, we tested the model with 1 mask, 2 mask, 3 mask, up to 10 mask, right? And this 3 mask actually turned out to be a better masking strategy. The optimal number of the number of masks. Okay, so, and this is a manually curated prompt. Now remember, we have some label data, right? Now we use this label data to further fine tune this this prompt. What does it mean? What does it mean? It basically means that we have this mask. After that, we have the corresponding embedding layers, and then the large language model. Then the ground truth. Based on the ground truth, we have some loss, right? The loss gets propagated till the end, right? And the embedding layers corresponding to the mask token will be updated, right? Again, a soft kind of masking strategy. So now let's see. Now we have, in the second part of this project, we wanted to understand how this prompt tuning, which is aligned to the task, which is argumentation mining, how it is useful. So this is the result. The first bar corresponds to the SMLM, our fine-tune strategy, and then long former and the prompt, right? The prompt tuning strategy. The second one is the long former, domain adapted long former. It was basically fine-tuned on the limited data set that we have for relation prediction, right? And then prompts, right? So if you look at these two results, right, the same model, long former, we use prompt in both the cases, but you see with SMLM as a fine-tuning strategy, the model performs quite better than a domain adaptation, the domain adapted model, which is quite obvious because we have very limited amount of data for domain adaptation. The third one is SMLM long former without masking. We just use a mean pooling strategy, right? Whatever we get, you basically pass it through a linear layer and the model will predict. You see, between first and third, right, mean pooling doesn't work. Prompt works better than mean pooling, right? The fourth one is a simple base long former without any domain adaptation, without any SMLM, and then prompting, right? And the fifth one is a base long former without any domain adaptation, but without any prompting. So if you look at these two things here, it also shows that prompt is useful, right? Compared to mean pooling, prompt is useful. Remember, here we are not using SMLM as a fine-tune strategy, but if you compare this with this, the first one, you see that SMLM further improves the performance. So takeaways, prompt-based models outperform mean pooling counterpart. In fact, if you look at the results that we obtained for span prediction, the one that we showed earlier, so this result was shown earlier. And if you look at the performance gap between SMLM long former and base long former, right? You see the difference is only 0.03, whereas here the difference is quite significant, 0.62 to 0.67. So even we observed higher performance gain in case of relation prediction compared to the component identification, and I think this happened because of this prompt alignment. Okay. The third observation was, as I mentioned, the SMLM models outperform base and domain adapted counterpart, right? And then so the takeaways from this part, this part is that your pre-training objective should be aligned to the. Remember, when I say pre-training, I assume that you already got a pre-trained model, then you are further fine-tuning. Okay. So your pre-training or the fine-tuning strategy should be aligned to the task that you want to perform. The prompt that you are writing should be aligned to the task that you are performing, and your prompt should also be aligned to the pre-training strategy that you have performed for pre-training your model. In our case, this was SL. Okay. All right. Now, moving to the next part. So we understood that prompt alignment is useful. What happens in case of cross-lingual prompting, right? Let's first look at the ICL paradigm a bit rigorous manner. So the ICL in context learning paradigm actually happens in the following way. You basically give the model a set of exemplars, demonstrators, right? And then a test set is concatenated, and you want to predict the corresponding level of the test, right? For example, let's say this is your ICL. Albert Einstein was German, some separator. Mahatma Gandhi was Indian, some separator. Marie Curie was dash, right? Your model should respond to this one by saying that Marie Curie was Polish, right? So here the important thing is as follows. Let's say instead of giving this kind of prompt or this kind of exemplars, if I had given something like this: Albert Einstein was a genius physicist, Mahatma Gandhi was an Indian, Marie Curie was dash, right? So model will get confused. Model doesn't know whether the response should be Polish or whether the response should be brilliant, right? So, I mean, someone can say that since Albert Einstein was a genius or Albert Einstein was a genius physicist, you can also, the model can also say that Marie Curie was brilliant, right? So how do you select these exemplars? That is very important for your downstream task. Okay. And we also need to understand that there is always a latent concept, right, which is hidden inside these prompt examples. The latent concept the model should understand the latent concept. For example, in this case, the latent concept is the bio, right? You want to understand the biography of this great personalities, right? Let's say instead of giving Albert Einstein was a German, right? You had given something like this. I love cooking, right? I love cooking. Mahatma Gandhi was Indian. Mary Curie was Das, right? Model will get confused. So the hidden concept the model should know what is the hidden concept. And when you write a prompt, when you write a set of exemplars, the example should also, you write an example in such a way that the concept behind the exemplar should be aligned to the task that you want to perform. Okay. So context, now in this case, context is these exemplars. Context and test input are similar in some sense. The notion of the task should be shared between the concept and the task that you want to perform. Okay. So in general, how we now think about a practical case, right? Let's say you want to do some certain task. Let's say the task is movie review prediction, sentiment prediction, movie review, sentiment prediction of movie reviews. And you want to design prompts, right? You want to design examples. How do you do? How do you write prompts? So remember, it is not that you have only one example. You have millions such examples. Now, for millions such test sets, sorry, not example, test sets. Now, for each of these test sets, if you start writing prompts manually, you are gone, right? So there should be some ways to basically extract these exemplars from a pool of exemplars or from a pool of training set, right? And then you design this prompt automatically for your downstream task. The downstream task is movie review, sentiment prediction of movie reviews. So what's the base simple strategy? The simple strategy is that you have a training data for selecting the prompts, your exemplar and the label, corresponding label. You choose prompts from your training data, right? This training data can be the training data on which your model was fine-tuned, or the training data is could be a different training data for your prompts, right? So you basically choose these prompt examples from the pool randomly. Then you create these demonstrators. So this is the pipeline. You have labeled data of source language. Remember, we are doing this in a cross-lingual setting. Source language is English and target language is Hindi. So you have a lot of such examples in the English language. You use some prompt selection strategy, assuming that the prompt selection strategy is random. You randomly choose prompts from your example, from your corpus. Then for a test input, which is Hindi review, you want the model to predict the corresponding sentiment, and your model will predict. Let's see an example. Okay. So can we do it better? This random strategy might not work. Can we do it better? So here is the idea that we proposed. So instead of choosing the examples from this pool, from the label data randomly, we wanted to choose those examples which are similar to the test data. Okay. And what we did, we used a simple sentence encoder, sentence transformer. Sentence transformer encoded the exemplars as well as the test set, right? And then we used a simple dot product kind of similarity. We extracted top key exemplars which are similar to the test set, and then we prepared the demonstrators, right? Very simple. Now remember, this is quite tedious because for every test set, right, if I assume that I have million size corpus for selecting the exemplars, for every test set, I need to do this dot product and choosing, and I need to choose top k examples, right? So just to, we wanted to make it fast. So we use this maximum inner product search strategy, which was already proposed by Google long time back for indexing. And that would help us select top k similar exemplars with respect to the test set. Okay. Let's look at let's take an example. Let's assume that the test set review is this. यह film मुझे पसंद नहीं आए. This is the review for which you wanted to perform the sentiment analysis, right? And in your data set, which is in English, you have these prompts, right? This movie touches my heart, positive. You know, this is a crappy piece of art, negative. GPT-4 has outstanding logical ability, positive, right? So if you had chosen examples randomly, you could have chosen the first one and the third one, right? As an example, the third one is not at all related to the movie review, the test set, right? So better to choose the first two, right? Because the first two examples are related to the test set for which you want to perform the sentiment, right? So using top k similarity, we could possibly choose the top two, prompts, examples from the data set. Now you just concatenate them. So you are preparing the demonstrators, right? So this movie touches my heart, positive, separator. You know, this is a crap movie, crappy piece of art, negative, separator. यह film मुझे पसंद नहीं आया. So this is the entire prompt. Now your model should predict that the label of this test set is what. So remember, in case of English, you have only two labels, positive and negative, right? In case of Hindi, you have two labels, which are acha and bura, right? Acha corresponding to positive, bura corresponding to negative, right? The label sets, these labels are also different from the label that you have in English, right? So how does the model know that the next word should be bura, right? The model doesn't have any idea. Remember, the model is a multilingual model, like that. Let's say the model is MT5, right? But still, the model doesn't have any idea about the labels of the test set. Okay, so top k examples is good, but how would the model know that the labels are this? Okay, remember, we do not have any prompts, any examples related to the target language, which is Hindi in this case, we assume. So to address this thing, what we did in between the prompt selection and target and test input, we added a task aligner. Okay, what is the purpose of the task aligner? The purpose of the task aligner is to let the model understand that good corresponds to acha, bad corresponds to bura. Okay, so for that, so this is the new part that we are adding to the demonstrator. So exemplars in Hindi, bad is kharab, bura, whatever, good is acha, right? And then the test set. So the hope is that with this, the model would not only know what are the possible tags, right? But also the transition, if you think of it, without this part, without this task aligner, right? You had like this, okay? You know, this is a crappy piece of art, negative. Then the next word is ye film. So the transition from negative to ye, right? The transition probability from negative, this is a normal sequence, right? Your model has already been trained on a multilingual corpus. Still, the transition between from negative to ya would be very, very less probability wise. The probability from this transition probability from negative to ya would be very less, right? So instead of this, if you add this and if you add the task aligner, the hope is that the model should be able to better learn the probability, right? So bad is kharab, good is acha, then from acha to ya. So the transition probability might be higher in case of this kind of prompt compared to a simple monolingual prompt or monolingual with some additional things, right? So we have two components, two contributions. The first contribution is to select top K exemplars. The second contribution is to come up with this task aligner. Okay. So remember, this task aligner was curated manually. Right now, we will see later if you use another model to come up with a better task aligner, what would happen result-wise. So we tested this model on 3 datasets: multilingual Amazon review corpus, cross-lingual sentiment classification, and Hattival dataset. We considered 11 languages, monolingual languages, and pairs of these monolingual languages. For example, English, German, Spanish, French, etc., and all the pairs, because it's cross-lingual. So English, French, English, French, English, German, German, Spanish. So there were 44 such pairs on which we tested our model. So in the abolition part, you see there are 4 variations: a simple random prompt selection, a semantic top K based prompt selection, a simple task aligner without using a top K selection, and then semantic top K plus task aligner, right? So you see, so this is a small, I mean, this is a summary of the entire example in the paper. There are these large tables, but you see that, random sampling is always bad. Semantic, the task aligner is very useful, and of course, semantic plus task aligner is the best, except for a few cases like, in this case, English German pair. And we in the paper we basically tried to justify why in case of certain pairs the model did not perform well. So now, automatically the question would be, why this kind of weird task aligner, right? The kind of aligner that we manually proposed. Why not some other kind of aligners? Okay. So to understand the impact of the aligner that we proposed, we did this kind of analysis. Now one baseline was just a random prompt, right? Without any aligner. The second one was this one, uniform label space. We just wanted the model to predict labels, corresponding to Hindi language, but the model is not aware of this acha bura, right? The third variation was task alignment by language information only. So in the task aligner part, instead of writing in this way, good is acha, bad is bura, we just said that, that the target sentence is Hindi. That's all. So the hope is that the model should understand that the target language is Hindi, and the model should, retrieve the corresponding labels related to Hindi. The fourth variation was task alignment via third language. Let's say, instead of saying that good is acha, bad is bura, I use a third language, which is, let's say, Bengali, right? And I say, the Bengali translation of good is bhalo, and the Bengali translation of bad is kharab, right? So in this task aligner part, we write in this way. Good is bhalo, bad is kharab. Okay, so the task aligner doesn't have any idea about Hindi, but task aligner now has idea about that something is going to happen in the cross-lingual setting. Okay, so a third language, which in this case Bengali, in our case, in our paper we use Spanish as the third language. The next variation was kind of an incorrect task aligner. We just randomly add whatever you want to add as a task aligner. And the last one is our proposed task aligner. You see that across all languages, our model performed quite well. Okay, so the last one performed quite well. One can now argue that you can use a model, you can use a multilingual, let's say MT5 model, to learn the task aligner automatically, right? Instead of manually adding a task. We did that. We used a MT5 model. We fine-tuned MT5 model on a masked language kind of prediction kind of task. And we see here the automated aligner based on this MT5 model performed not as good as the task-based aligner, in fact, our model. But the good part, the good news is that automated aligner is better than the random prompting. So it basically indicates that this task alignment component actually helps you, right? I mean, you want to use a manually curated task alignment, or you use a automated aligner like MT5 for this task alignment curation, right? Creation. This automated aligner is also quite competitive to the semantic prompts. Semantic prompting. What is semantic prompting? Semantic prompting is basically the top K exemplars that we basically fetched from the corpus. But it fails to incorporate any task-specific signals, therefore failing to beat the task-based alignment that we manually curated. Well, we are not saying that this automated aligner is perfect, because one can come up with a better automated aligner. Remember, the end goal, of course, would be to come up with better automated aligner. So, of course, why in this case did this automated aligner did not perform well? Because our underlying model was XGLM, right? We basically did all this prediction task on XGLM, which is a billion size model, and MT5 model was used for automated aligner. The pre-training distribution was quite different. Therefore, one must not hope that this MT5 based aligner can outperform a manually curated aligner. Okay. So what are the takeaways? The takeaway is that we need an efficient prompt aligner, prompt design mechanism we should be aware of the pre-training strategy and as well as the downstream task that we want to perform. Alignment via simple measures like semantic similarity can boost the performance, as we have seen in case of top K retrieval. And specifically, if you use cross-lingual setting, then the notion of task needs to be transformed or encoded within the context that you were providing the model. Okay. I will take 2 minutes to just introduce the lab. So we are doing different aspects of large language model. This is the team working specifically in large language model in the lab, and we are interested in problems like this. We are working on a physics inspired large language model. So in 2021 NeurIPS paper, we showed how one can think of large language, a transformer as a multi-particle dynamic system. And we basically showed that if you think of it as a multi-particle dynamic system, it would reduce the parameter size significantly. We're also working on brain-inspired model based on some notion of entropy. We are working on improving the reasoning ability of large language models. There's a concept of layer editing, right? We're also working on this and some other aspects of large language models like model distillation, cross-lingual prompting, vision language model, and so on and so forth. We, along with this LLM-based research, you also work in graph neural network, particularly graph transformer, and how we can, kind of use the modern advanced version of language models into graphs. And applications, we are focusing on mostly 2 major applications: cyber informatics, where we are looking at hate speech, misinformation, other kind of cyberbullying. And we are also looking at how we can use large language models for mental health, particularly for mental health, kind of addressing different aspects of mental health. We are also working on using this large language models for text summarization dialogue systems. With this, I would like to thank, and if you have any questions, you can ask now, or you can email me. This is my email ID. we are hiring masters, PhD, postdocs in the lab. So feel free to reach out to us if you have any query. Okay, thank you very much.
Yeah, thank you so much, Professor. It was actually very insightful, and Andre had tweeted long ago that the hottest programming language is English. Ultimately, it all boils down to how well you write your prompts, and this is pretty insightful. And we do have some questions. Probably I'll share that now. So the first question is from Vipul. He has asked, can the data for SMLM be curated automatically using some heuristics?
The data is, remember, the data was curated from Reddit. The data was a Reddit dump. It was created automatically. On top of the Reddit data, we just identified the markers manually and semi-automatically, which are responsible for the downstream task, which is argumentation mining. Now, you can of course think of some heuristics to identify your mask, because remember, this mask, the phases that you want to mask, these are task dependent, and of course, if you have better heuristics to identify the tokens that you want to mask, that would be great.
Okay, sure. The second question is from Govind Soni. What extent can the use of prompts in pre-training replace or minimize the need for fine-tuning on specific downstream tasks?
That's a good question. And so far, if you look at the way people, perform the prompt-based exercise, is that they use a pre-trained model, then they write a soft prompt, and then using a tiny bit of fine-tuned, the tiny bit of training data that you have, you basically fine-tune your prompt. And the same strategy was also used in our case, right? I would say if you just want to get rid of the fine-tuning part, assuming that you have absolutely no data absolutely no data related to the downstream task that you want to perform, you should be very, very good in designing the prompts, right? The kind of research that people started working on these days is that, can we think of a prompt, a separate data set which contains only prompts, right? Now, remember, these prompts may not be related to the downstream task. These prompts can also be generic, right? If we come up with a better data set where different types of prompts are curated for different tasks, right? The hope is that you may not need to do fine tuning at the end. You just use the prompt, right, for your downstream task. But I think the space is still open. There has not been any specific work on particularly designing prompt without using any fine-tuned data.
Okay, he also has a follow-up. So are there any limitations or drawbacks to solely relying on prompts, and how can these be mitigated?
Yes, absolutely. There are lots of limitations. Remember, prompt engineering, now, so the way a human writes a prompt, right? We assume that whatever human writes, that's the optimal prompt for the model. But we do not know what's the optimal prompt for a model. Human thinks that this is the optimal prompt. But for model, the optimal prompt is completely different, right? So prompt-based, fine-tuning has a lots of limitations. So we generally assume that human-based, if you come up with a prompt data set from human labelers, that would serve as an optimal prompt from the label, but that's wrong, right? So efficiently coming up with an optimal prompt for a label, for a particular model, for a downstream task is extremely difficult. And the notion of short prompt, continuous prompt actually point towards that direction. How can we how can we come up with an optimal prompt for a particular task? So prompt engineering is good at a certain level, at a certain extent, but I would say, you need some sort of fine-tuning data set for further fine-tune your model.
Okay. So the next question is from Vipul again. So why task aligner is really important as seen in ablations? The model should implicitly know these simple mappings that acha means good and kharab means bad, right? Why giving this trivial and redundant information should be a really critical step?
So that's a very good point. Remember, it is not trivial for a model to understand that the next word for a Hindi task, for a Hindi review, the next word is going to be acha or bura. How would the model know that the next word is acha or bura? It's not possible. The next word may be kharab. The next word may be, some synonyms of acha, right? So the label space, so acha and bura was just an example. What I wanted to say is the label space for the test language is very, very different from the label space of the target of the source language, right? Now, if you do not let the model know this alignment, right? You don't expect, you should not expect that your model would exactly predict the label, right? The label of the test language. Remember, one can say that, okay, I don't need this kind of task aligner. I can think of a verbalizer. A verbalizer, what is a verbalizer? A verbalizer is basically a module which works on top of the word that was predicted by the task, the model, and then the verbalizer basically maps that word to the label, the test label, the test labels, right? But remember, the verbalizer also needs to be trained, right? So therefore, the models, at least the experiment that we did, where it was basically we showed that this kind of task aligner is very important. The other reason is that if you look at the transition, as I mentioned earlier, right, some English exemplars and then certainly a Hindi sentence, right? The transition, remember, in the optimal case, your prompt should be the topic distribution in your in context examples should be same as the topic distribution that is there in your training set, right? Now, it is very difficult to come up with a prompt with a topic distribution which is same as the topic distribution present in the training set, right? Therefore, we're using this task aligner. We kind of enable the demonstrator to basically add exemplars which for which the topic distribution should be same as the topic distribution in the training set. So task aligner is very important.
Okay, got it. So the next question is from Hima. So at the time of testing, is the user expected to give the prompts in the predefined format with the task aligner and the other inputs?
Yes. So in our case, as you have seen, we have curated the task aligner manually, right? But remember, in the conclusion, I mentioned that the end goal will be to come up with an aligner automatically. So MT5 based experiment that I mentioned, that was the baby step towards that automatic alignment, task alignment. But we are currently working on making this task aligner even better for different downstream tasks so that it would not be a manually, the task aligner should not be manually designed.
And what may the model implicitly learn here? Like after, this is the follow-up of the previous question. Like when we use aligner with other inputs for prompting, what is the model implicitly learning from that?
So the model is learning, as I mentioned, the model is learning two things. The model is learning the topics, underlying topic, right? Which is the topic should be similar to the task, to the test set. The Mahatma Gandhi example that I mentioned, the topic, the latent topic was basically bio, right? And the second one is that through this aligner, you are letting the model know the kind of labels that the model should predict, the test labels, acha and bura.
Okay. And we just have two more questions. So the next question is from Shobhan. Have you used COT prompting in your experiment? Does this COT prompt play any role in boosting the performance of cross-language LLMs?
That's a very good question. So yes, so chain of thoughts prompting is something that we are currently working on. Again, this is a follow-up task that we are currently working on. And the hope is that the chain of thought based prompt might be, should be better than the kind of prompt that we have shown here.
Okay. And the last question is from Sakib. Rephrasing the prompts in different way produce different sentiments for the same sentence. Does the semantic similarity of prompts not play an important role in the results?
Can you read it again? Sorry.
Yeah. So rephrasing the prompts in different way produce different sentiments for the same sentence.
Right.
We are using semantic similarity of prompts, right? So is it not playing any role in the result?
No, this is playing a role. So, that was the selling point, right? So semantic similarity based, semantic similarity based choice of prompts from the data set, from the prompt data set, right? That was the key point of the second part of the talk, right? So if you choose the prompts which are similar to the text set, right? In terms of the concept, right? The topic, right? That would automatically give you the boost, right? So that's why I mentioned that, in the bio kind of, if the task is to predict the bio, it should not happen that, one of the exemplars is, let's say, I eat rice, right? I love Chinese food, positive, right? Or something like this. So the exemplar should be similar to the task that you want to perform, the test set.
Great. I guess that's all we have for the Q&A. And thank you so much, Professor, for patiently taking in all the Q&A right after the presentation. And for all the attendees, thank you so much for patiently waiting on the call till the end. And we also have a Slack channel. Probably we'll send you a mail with all the information so that you can, be part of the Slack channel, where we'll be posting a lot of information about our upcoming talks and initiatives. And thank you so much once again for joining the talk. Yeah, I think we can end the session now. Thank you so much.
Thank you very much. Thank you. Thanks. Bye.
Thank you.
It was a fantastic talk.